Hello everyone, this is Dr. Feng Wang from my home, and we are going to continue the discussion of aldehyde and ketone molecules. But before we uh, discuss the regular aldehyde and ketone reactions, first I would like to share with you two examples from exam 3. So some of you proposed me to use these two as examples how we solve organic chemistry problems. So the first one is both questions are synthetic questions. So the first one is to synthesize these molecules. It's from a benzene. It's basically benzene attached to a amine group and methoxy, methyl ether methoxy groups on both sides. So the correct answer is first you do the chlorination of benzene with the catalyst, the iron chloride, to the chlorination aromatic chlorination reaction. This is a pretty simple reaction. You should know that. The second step is to do the nitration reaction with the nitric acid and a strong concentrated sulfuric acid to introduce the nitro groups. We know the chloro here is the ortho and the para director, so we can introduce the nitro group and the para position. The next step is very critical. We use the sodium methoxide. Sodium methoxide is a nucleophile because the oxygen bears a negative charge, so it is nucleophile. This reaction is electrophilic substitution reaction. The second reaction also an electrophilic substitution reaction. If you review the detailed mechanism, so you will see these first two steps reactions are all electrophilic substitution reaction. But this step is a nucleophilic substitution reaction, again because this is a strong nucleophile. So why we can do the nucleophilic substitution here is first, the chloro atom here is very good leaving group. The second driving force actually is very important is the nitro group. We know nitro group is very strong electron withdrawing group, which means to pull electron away from the benzene ring. Or in other words, the nitro group makes some positive charge here around the benzene ring. Again, strong electron withdrawing. So whenever you generate a positive charge around here plus a good leaving group, so that make the electrophilic substitution reaction possible. So the methoxy group will attack this carbon. Chloride serves as a leaving group to make this nitro methoxy benzene molecule. So next step is very simple. It's just the reduction reaction of the nitro group reduced to amine group. So this is the right procedure to make this target molecule. So I will not share with you each choices or each options you have in the question, but I just share one with you, the typical one here. So we can do chlorination reaction just as the first one, that's not a problem. The next step, do we need to do the nitration first or do we do the nucleophilic substitution reaction? We can use this is strong nucleophile, this is good leaving group. Here, whenever you compare this molecule and this molecule, you see, this is a very strong electron withdrawing group, generate some positive charge here. But there is no strong electron withdrawing group at all in this molecule, chlorobenzene. So this is strong nucleophile. It would be hard to attack this carbon because benzene we have 6 electrons here, so it's easy to do it electrophilic substitution rate, but it's hard to do the nucleophilic substitution rate. There is no help. So this reaction, basically, I never did this reaction, but I did a similar reactions for probably around 10 years. Very likely we do not have reaction from this step. That's why we have to do the nitration first to generate a very good substrate to do the nucleophilic substitution reaction. This is one of the reactions in exam 2. The second question, I want to use examples to share with you, also proposed by some of you. A synthetic question. So we want to use the benzene to make this alkene benzene bromobenzene. So the first step to do the Friedel-Crafts reaction, we used a bromoethane, aluminum chloride as the catalyst to introduce the alkene groups, the ethanol group, to the benzene ring. So ethanol group, alkyl groups is the matter para director. So then we do bromination. We can introduce the bromine atom into the para position. That's no problem. So the next step is to do the radical reaction. So whenever you see NBS in your mind, this is bromine. Whenever you see H-mu, that's the UV light. That means the radical reaction. So bromination of this molecule with a radical mechanism, always the alpha position, the first carbon attached to the benzene. This is similar to the allylic carbonyl, allylic radicals. This is the position to do the bromination with the radical mechanism. So basically, we introduce the bromine atom at this alpha position. So the next step, this is tertiary butoxide. I can guarantee you, this is tertiary butoxide, tertiary sodium will be all organic chemistry, exams. That this is a strong base, but it's not a nucleophile. So this is a simple E2 elimination reaction because this is strong base. To do the elimination reaction and generate the alkane here. And then this step, basically, you can forget about this benzene. It's about this bromine and one of the hydrogen here to generate alkanes. This is the right procedure to make the target molecule. As the previous example, I don't have time to share with you all the choices you have, but here just one of them. You can bromination the benzene ring with the bromine and this Rn bromide. This is not a problem to introduce the bromine atom to the benzene ring. The second step is also this is also a Friedel-Crafts reaction, but this is the ethylation reaction. Introduce the ketone groups here. So this is basically, if you count carbons, basically we have 1, 2, 3 carbons. We introduced 3 carbons to this benzene ring. It is a ketone here. We can do a reduction reaction, and we can do whatever we want to make. But one thing obvious here is you see this alkene here, only 2 carbon, CH2. Whenever we did this Friedel-Crafts reaction, we already had 3 carbons here. It's probably hard to reduce one of the carbon from this to the targeted 2 carbon. So basically, we can stop here. Okay, again, I just share the correct answer and one of the answers from your options. If you want me to share with you more about other options, whenever you have a question, you're welcome to text me or send me an email. We can have more discussions. All right, let's continue the reactions from aldehyde and the ketones. So in this section, I'm going to share with you the aldehyde and ketones reaction with the amines, either primary amine or secondary amine. The first one is the aldehyde or ketone react with the amines. We normally use the acid, mild acid, as the catalyst. The reaction product is called amine. This is the reaction product. It's called amine. Basically, there is a carbon nitrogen double bond. This molecule is called amine. And water is the side product. Well, I'm a big fan of the mechanism. I wish I try my best to help you to understand the fundamental mechanism of organic reactions. Well, that's again, is the education is to understand things, not remember things. However, if you want to move faster, I can share a secret with you here. So we have an aldehyde or ketone plus a primary amine. Basically, we are going to lose one water, 2 hydrogen from the primary amine, 1 oxygen from the aldehyde or ketone. Thus, the molecules we are going to lose water. Then the rest is the amine. Basically, you just cut from here. This is oxygen. You cut from here. This is hydrogen. Forms water, and it forms carbon nitrogen double bond. The rest of both molecule remains. This is the final product, amine. And I have 2 examples here, either a cyclic ketone or just a linear ketone react with the a primary amine. It could be a linear amine or it could be a amine with a cyclic side group. That we have amines, carbon nitrogen double bond. Mechanism. Again, the carbonyl carbon here bears positive charge, and lone pair electrons, always nitrogen has the lone pair of electrons, so always want to share with someone who bears a positive charge. To form addition product here, it is the obvious reaction is to transfer 1 hydrogen from here to make neutral compound. This is called a carbanoamine. This product is amine, still amine. This is hydroxyl group, OL, carbon in the center, carbanoamine. This molecule is not very stable, so the next step is, because we have a mild acid as the catalyst, the protonation of these hydroxyl groups form a very good leaving groups, water, to generate a carbon cation here. Because we have a carbon cation, the carbon cation is not very stable. 2 electrons, 9 shared of electrons will fill in this position to neutralize this carbon cation. That's why we have this carbon nitrogen double bond. However, at this moment, the nitrogen itself bears positive charge. And the next step, because of the nitrogen also attached to the hydrogen always easy to move around. The next step is water serves as a base to do the base acid reaction, or this reaction, the result of this reaction is the deprotonation of this nitrogen. So this is the final product. It's called amine. So if you remember my secret, oxygen from a aldehyde or ketone, 2 hydrogen from a primary amine react, forms water, and a new carbon nitrogen double bond formed between the ketone part and the primary amine part. That's my secret. Hope to help you a lot. And the next reaction is called enamines, the formation of enamines. The enamines then basically is aldehyde and ketone, the same from the amine reaction, react with the secondary amine versus the primary amine. So the final product is carbon. We have carbon. We don't have carbon-nitrogen double bond. We have carbon-carbon double bond. We have a carbon-nitrogen single bond. This is the secondary amine part. Here I also have two examples. Could be any kind of a ketone or aldehyde. Has to be ketone or aldehyde. React with a secondary amine. Amine attached with one hydrogen, two alkyl groups, and one hydrogen. This is a secondary amine. So we don't have two hydrogen here to form a water with the carbonyl groups here, but we are still going to lose one water molecules. So if you want to know my secret is, here we are going to form carbon from a carbonyl group, and nitrogen. This is a new bond, carbon-nitrogen bond, and a carbon-carbon double bond. Carbon, the first carbon is carbonyl carbon. The second carbon is the alpha carbon of this carbonyl carbon. You see, the alpha position, either this position or this position. This two carbons will have a pi bond or carbon-carbon double bond. See, this is the amine part. We are going to have a new bond, carbon-nitrogen new bond, and a double bond between carbon-carbon. This first carbon is the carbonyl carbon. The second part carbon here is the alpha position of this carbonyl group. So those two carbons, we will have a new carbon-carbon double bond. That's the final product. It's called an enamine. So this is N, carbon-carbon double. N, amine. Amine, you see this part is still amine, so that's why this molecule is called enamine. The mechanism is similar to the imines formation. The first step also, the nucleophilic addition reaction, because of the lone pair electrons from nitrogen attack the positively charged carbon to form addition reaction product. The protein transfer from nitrogen to oxygen form a neutral bond. The next step also similar to imines formation, the protonation of the hydroxyl group to form a very good leaving group. So whenever we form a very good leaving group of water here, these two electrons, the lone pair, will fill this position to form a carbon-nitrogen double bond. Here, carbon-nitrogen double bond. This is a different. Here, this nitrogen has two alkyl groups. Alkyl group, they are non-leaving group. So in the case of primary amine, this nitrogen has hydrogen. We can depronate this nitrogen here. But here we have two alkyl groups. Alkyl group never serves as a leaving group. So we have to figure out another way to get rid of, this positively charged. That's why we go to the next one. This is the carbonyl carbon. Then we go to the next one, that's the alpha position. This alpha carbon has a hydrogen here. Because of the positive charge here, this hydrogen has some acidity. So the next step is the acid-base reaction. Water serves as a base to do a water-base reaction. So protein react with water. The two electrons move to this position, and this pi bond, two electrons move up. So nitrogen has the lone pair, but a new carbon-carbon double bond is formed from this reaction. So this is called an enamine. And I want to share with you each step in this enamines formation or imines formation. Each step is reversible. So we can go this way, or if we have this molecule, we just dumping on this little bit of mild acid, we can we can go decompose this enemy to the original molecules, the aldehyde or ketones, plus a secondary amine. But what we have in the how we do this reaction in real world. So this is the how we do it in the real world. If we really want to do this, we want to synthesize this enemy. Okay, we can decide what kind of a ketone we need, what kind of secondary amine we need. We do this reaction. But because each step is reversible, whenever we form this product can go back to the starting material. What we did in the real world is whenever it is formed, we isolated this molecule, enemy molecule. We use the physical or chemical techniques to isolate this molecule. So we keep on all the reaction moves from this to the final product. We are going to make a more and more enemy product. Or if we want to make do the reaction the reversed way, we have enamine. We want to make a ketone, the secondary amines. We just dump in enamine and a little bit catalyst of formaldehyde acid. So it will move to this way. So whenever a ketone or a secondary amine formed, we have to remove the product from the flask. That will keep the reaction moving from enamine to ketone and secondary amine. And this is just how we do the reactions in real world. All right, the hydrolysis of amine and enamines, because I just said each step is reversible. If we have an imine or enamine with a little bit of catalyst acid, we are going to form ketone, primary amine, ketone or aldehyde, or secondary amine. So I'm not going to discuss the details of this reaction. Basically, it's these reactions are reversible reaction. So the next reaction I want to share with you is the hydration of aldehyde and ketone. Hydration, you can figure out hydration is basically water. It's basically ketone and aldehyde will react with water under either acid condition or base condition. So the final product is a diol, is two alcohols, but this is two alcohols attached to the same carbon. So this is a special diol. It's called a germ diol. So basically, it's a hydration product by either aldehyde or ketones and two hydroxyl groups attached to the same carbon. Formaldehyde react with water, form the hydrate. Basically, it's two hydroxyl groups attached to one carbon. This is aldehyde with two carbons. It can do hydration reaction. It's two hydroxyl, again, it's German diol, two hydroxyl group attached to one carbon. Well, when the aldehyde or ketones react with water, they have a different reactivity. I remember beginning of the chapter we discussed the reactivity of aldehyde and ketones. This is the trend. Because of the steric effect, ketones in 2R groups much bigger than the hydrogen. So this molecule is more stable, or is, in other words, this is less reactive towards water. But this one, because only two small hydrogen atoms, it's less stable, but more reactive towards water because steric effect is two hydrogens so small. A second reason I shared with you before is because of the charge. These two methyl group, electron donating group. They are electron donated to the carbon. This carbon bears positive charge. So when you have a positive charge, you're not stable. but you have two good neighbors help you to stabilize you. So this one is the less reactive but more stability. But this one, aldehyde, because these two hydrogens will not donate any electron towards this carbonyl carbon. So this carbonyl carbon is very reactive towards the addition of water. So if it's hard to have pure formaldehyde in water. Basically, the majority of the molecule of formaldehyde in water, this is the majority. So for the ketones, if you add some water in ketone, well, you have only less than 1% of these German diols. Majority is water, ketone is water. Ketone is ketone, water is water. They are totally different. Only less than 1% react. So again, there are two mechanisms to do the hydrations of aldehyde or ketones, either base mechanism or the acid mechanism. It's very simple. We have a base, a strong nucleophile attack. This is negative charge, this is positive charge, to form oxygen anion. Oxygen anion can do the protonation to form a German diol. This is a base mechanism, very simple, very straightforward. Acid mechanism of the hydrations of the ketones or aldehyde is slightly complicated, but I think you can understand, the whole process. Normally, if you have a carbonyl groups and you have acid catalyst, the first step is very natural. It's just a protonation, two lone pairs, protonation of this carbonyl oxygen to form a carbon cation actually. The next step, is the carbon cation has to figure out a way to neutralize this charge. So it's going to react with one of the two lone pairs electrons in water to form an addition product. And the next step, oxygen has to figure out a way to get rid of its positive charge. Basically, water serves as a weak base to react with this strong acid to form the two hydroxyl groups here. And this is the acid catalyzed process of the hydration of either ketones or aldehyde. I have a simple word here. It's called PAD. PAD stands for protonation addition deprotonation. Whenever you have this PAD process, probably good for many aldehyde, ketones, or carbonyl compound. Protonation of oxygen, that's protonation, addition, water, addition to the carbonyl cation, then the deprotonation of one of the two hydrogens in water molecule to form a new product, PAD. So whenever you see carbonyl acid condition, think about PAD reaction. Alright, that's all I want to share with you today, and we are going to discuss addition reactions of alcohols to aldehyde ketone in the next class. Thank you.